just sort of standing there. You guys are so good. All right, thanks for coming, everybody. So this is the last in sort of a series of events we've been having that we're calling the Air-to-Water Heat Pump Summit. So I know, was anybody involved with any of this stuff yesterday? I guess, well, yeah, actually, yeah, some you were there. So we had an all-day training focused more on sort of residential, maybe small commercial applications of air-to-water heat pumps, led by John Siegenthaler. That started at like 7:30 to 5 almost. It was a long day. And then we had a fun evening event. We had 9 different manufacturers from all over North America who joined us to sort of give a quick little mini expo on some of their products, and it was pretty cool. We had a little event where we had these guys each had 5 minutes, hard stop. Brian Sweeney was there with a coach whistle, and they all did exceedingly well under pressure. So I think both of these guys I have here today. We have Daniel Silva, who is representing Airmec. Who's going to tell you a little bit about some of their products and a little bit about some of the applications that they have. We also have Benoit who's going to be following up with another product. He represents Thermoatlantic, so we'll hear a little bit more from that. Yeah, so I guess these guys aren't really clear exactly who's in the room. But maybe just really quickly, we've got what? We've got engineers, we've got, who else are we representing? Craig, housing, multifamily. We've got some of our customer support folks who are really sort of our, Renaissance people that have to know a little bit about everything. And I guess we've got some program managers, such as myself. Anyway, I guess I'm just gonna hand it over to you. We also have a bunch of folks on the phone. I don't know who's on the phone.
We have 11 people.
11 people on the phone?
So.
Okay. So there are more people out there listening and watching. So the format for today basically is we're gonna try to do about 30 minutes a piece and then try to have some Q&A. We do have 90 minutes. And we even have a little extra time if things need to spill over. But yeah, and I do apologize, at the swap over point between the two, we may have to have a little break just because there's some technical complications around it, but we'll get it sorted out. So stick with us. All right, without further ado, Daniel.
All right. As far as speaking, do they need to be near?
As much as possible. Are people able to hear relatively well? Okay.
Okay, thank you all for coming in today. My name is Daniel. I've been working with Armec since 2006. I've been working with them in Europe. I joined the North American operation a couple of years ago. And we're going to show some slides talking about Armec, and then we're going to show some of the products that we have that are applicable for these type of applications, and also some case studies. So Armec is one of the oldest manufacturers of air conditioning equipment in Europe. They were founded in 1961, an Italian company, still today a family-owned business. That's been kind of the secret of the growth of Armec. They've been steadily growing the company over the last decades. And they've been doing heat pumps for many, many years. Heat pumps, it's a very known technology in Europe. And they've been in the top of that game for many decades. Everything is still done in Italy. They have several plants in Italy. This is the Armec plant where they do all the heat pumps and all the chillers and fan coils and the products that they do, the main products. It's between Verona and Venice. Everything's shipped overseas here. Armec is present worldwide. In North America, they're present for about 12 years. So not that long ago, it was part of their expansion plan. They're one of the top 3 players in Europe, so they didn't have much market share to gain there. So they started to look into other markets, and that's when they started to look into North America. So we're here for about 12 years. We don't have all the products that are available in Europe, but we have a lot of products already. Every year we have more products and new solutions that are designed specifically for this market. That is, of course, different from the European market. So talking about heat pumps, in North America we have a very wide range of units available, from 2.5 tons to 260 tons. So from very small residential type of units to large commercial applications. We have jobs with 5 times 150 tons or something like that. So we're talking about very small scale to very large scale applications. We're going to focus the presentation in 2 of our products. This is our latest generation heat pump that we call Armec NRK, and it's one unit that was specifically developed for heating applications. It's a reversible cycle heat pump, but it is a unit for cold climate regions, and we've been starting to see a development in the market that is providing more solutions for cold climate regions because there is a demand for that. Like 10 years ago, the solutions that were available in the market were nowhere near what we have today. There were a lot of limitations in heat pumps. We lose a lot of capacity at low ambient temperatures. The operating limits were not what it is today, and there is a demand from the market to have other type of solutions. And the manufacturers start to provide the solutions to that specific needs, to those specific needs. So that's how this unit came about. We call it a latest generation air-cooled heat pump. It is a unit optimized to work in heating mode. Historically, it wasn't like that, but now you start to see heat pumps that are optimized to work in heating mode instead of optimized to work in cooling mode. It means that you have counterflow in the heat exchanger in heating mode, and you have better efficiency in heating than in cooling. But most important is that in these units we have extended operating limits compared to traditional heat pumps. We have a range in these specific units from 9 tons to 40 tons. So kind of limited to 40 tons, but we can always put several units together to 9, so you can deal with large scale jobs as well. So this was what I was talking about. You see the operating limits of a standard heat pump. It's this green line, maximum living water temperature 131, down to +5, but you have this big derate when the ambient temperature starts to drop. More or less about 25 Fahrenheit or around that temperature. We cannot do 131 anymore. You start to lose capacity, and more than that, the compression ratio becomes too high, so the unit cannot deliver the same living water temperature anymore. Of course, this is a limitation for cold climate regions. You want to have the unit to be delivering as hot water as possible, and for the coldest temperatures as possible. So now we have this new solution, and then you see it has a much more extended operating limits. We can do up to 149 living water temperature, so allows us to deal with other type of applications. And more important than that, we can do 149 down to 14.5, and we can also work down to -4 Fahrenheit, still delivering 131 Fahrenheit living water temperature. So it's a solution for cold climate regions, and it's something that the industry has been giving as a response to the market demands. So how do we do that? It's still a heat pump or reversible cycle heat pump, can do cooling or heating, but it has a little bit more of a complex refrigeration circuit. We need to add injection line in the compressors to be able to work with the higher compression ratios. So we'll have a refrigeration circuit that is something like this. We have the compressors, the reverse cycle valve. From there, we go to the plate heat exchanger where we get hot water for our building or for our process application. Then we have this thermostatic valve and the external coil where we do the evaporation. Then you have these added components that are the injection line and are pretty much the secret to work with high compression ratios and low ambient temperatures. So what we achieve with that is that first to do 149F living water temperature with R14A, you need to have some sort of control. I lost the pointer, but it doesn't matter. We need some sort of control on the discharge gas temperature because otherwise it will be too hot for the compressor operating limits. So we'll have that injection line to bring that discharge temperature down and keep it under control. And we'll also be controlling the superheat. So we're basically adding some complexity to the unit. To the end user, it's just like a reversible cycle heat pump. You have water in, water out, up to 149. You don't need to care what's behind the machine. But what's behind the machine is these. These are new compressors, fairly new compressors from Copeland. And they recommend this refrigeration circuit to work with these higher compression ratios. More important than that, it's what you get from this type of machine, not as much how you get it, but what you get from it. So you get higher COPs, The top line is the COPs of this machine, and the bottom line of a traditional air source heat pump. So you see significantly higher COPs and the ability to work with lower ambient temperatures. So this is at 131 living water temperature, and COPs down to -4. If you are able to work with a lower living water temperature for radiant applications, the difference will not be as big because the compression ratio is not that big. But when you go to low ambient temperatures, you see that huge gap between the COP of a traditional heat pump and these latest generation heat pumps. So even at the radiant applications, and in cold climate regions, you'll see a huge improvement in terms of COP. So basically, this is a new machine. We have it for about a couple of years. And it is a response to a demand for cold climate solutions. You have much higher COPs at low ambient temperatures, so you can run your heat pump more time during the year without bringing the boiler on. The balance point will be at lower ambient temperatures, so you'll be saving more by running the heat pump longer in the year instead of need to bring your boiler at 0 Fahrenheit or 5 Fahrenheit or something like that. Yeah, this is one of the jobs we've done with these units. It's in Denver, where we have 4 of these units put together. Like I told you, you can have up to 9 together. So in this case, we have 4 40-ton machines, provide 160 tons of high hot water delivery. And then we have another heat pump, another 160-ton heat pump that can do lower temperature hot water. So this was in Denver. They have a design temperature of -3F, so these units can run year-round. The limit is -4. That's the written limit. Normally they can go a little bit lower, but well, we always put some safety factors into the operating limits. And this was a carbon-free project, so the building owner wanted to get away from fossil fuels, and this was a perfect solution for that application. So we have 4 units that deliver hot water up to 149 for what they need for process and massive hot water, and then we have another heat pump that does cooling and heating for space heating and cooling.
Do you have any heat exchangers, or do you have heat trace to protect it against freezing?
Yeah, for sure. So the heat exchangers are always heat traced. If you want to have for example, if you have a unit with the pumps incorporated, we can have the pipes heat traced as well. But anyway, in places like these where the temperatures are so low, I always think it's a bit risky to run water, even if it's heat traced, because if you lose power to the machine.
Yeah, if you did a generator or something.
Yeah, exactly. We can do that as well, have a dedicated power supply for the heat tracing circuit. Okay, so we're going to move now to a different topic, well, same topic, but different product. This is a unit that is different from the one I talked about. I talked about a reverse cycle heat pump, a unit that can give you chilled water or hot water. You reverse the cycle to do one or the other. I'm not going to talk about heat recovery heat pumps. So it's a different product that can give you just cooling, just heating, or the 2 things at the same time. And this is the solution we've been seeing as a really interesting solution for multifamily housing and also for commercial applications. In this case, we have a range from 13 to 240 tons, so very wide range of units available. And the units are a bit different from the one I was just talking about, mainly because we have 2 plated exchangers in these machines. So you're going to have one for chilled water and one for hot water. Then you always have at least 2 circuits and multiple compressors per unit to be able to handle all the operating limits. We can put the pumps inside the unit to simplify the installation. We do that a lot of times. Really simplifies the labor to install the units. We can put the pumps for both circuits, chilled water, hot water, and even the expansion tanks. You see, if you want to have heat tracing, these pipes that you see here, they will be heat traced as well. So these units can work as a chiller, providing chilled water only for the building, can work as a heat pump, providing just hot water for the building, or they can provide both at the same time. So if you have a building where you have needs for cooling and heating simultaneously, you will always be having higher efficiency from this machine, because whatever is the smallest of the 2 loads, you get it for free via heat recovery. So you can have the 2 circuits in cooling and heating, or you can have one circuit doing one mode and the other doing another one to adapt to unbalanced scenarios that you're going to have in a lot of times during the year. The unit will adjust to whatever are the loads that you have in the building. So you see you have two heat exchangers. When you are in chiller mode, you come from the compressor, reject the heat on the condenser coil, cross the thermostatic valve, do chill water for the building. If you reverse a cycle to heat pump mode, now you're doing hot water in a different heat exchanger, so it's not like a traditional tube pipe reversible cycle heat pump. Now you're doing hot water here, so you come from the compressor, do the condensation here, and do the evaporation on the external coils. And the really interesting thing about this unit is that when you have those simultaneous loads, you will not be rejecting or getting any heat from the ambient air. You are pretty much working as a water-to-water machine, providing cooling and heating simultaneously without rejecting anything outside. So you are pretty much doubling the efficiency of the unit when you are in this operating mode. You can see, lost the clicker, so I'm gonna show you.
Stop working.
Yeah. Just the point.
Oh, the pointer's not working.
Need a big stick.
Yeah, okay.
Sorry.
Anyway, it's gonna work. So in this, we're showing a selection output of the machine. Over there, you have the cooling output, just cooling. You see you have a ER of 9.57. On the bottom over there, you have the heating output, just heating, air source heat pump with a COP of 2.7. When you go to simultaneous mode, cooling and heating, your COP goes to 5.6. So you're pretty much doubling the efficiency of the machine because you're providing two things at the same time and pretty much the same input power. You have the same compressors running. Instead of rejecting the heat outside, you are producing hot water and chilled water at the same time. Even at part load, this graph could be a little bit complicated to read, but you have basically heating load percentage, cooling load percentage. Over here you have 0% cooling and just heating. At these conditions we have a COT close to 4. When you go to all sorts of simultaneous loads, let's speak for example 25% cooling, 75% heating, you see your COP is already 8. So you can get COPs up to almost 10 with this type of machines at certain part load conditions. Another very important thing about heat pumps and these units or any heat pumps in general, it's a defrost logic. Defrost is something that any heat pump will have to deal with at some point, typically between 35 Fahrenheit and 45 ambient temperatures. It's where it's the most critical period for defrost in heat pumps. And like I said, any heat pump will need to do defrost cycles now and then. So it's not a matter of doing defrost or not doing it, because everybody's going to need to do it. It's how you do it. And Armic has been doing heat pumps for a long time. And they understand that defrost is a very important thing when talking about heat pumps. So they developed what they call the intelligent defrost logic. And it's a logic that allows them to do defrost cycles exactly when the unit needs to do it. If you know what defrost is, it's you're producing hot water for your building, and at a given point you need to reverse the cycle to cooling to melt the ice on the coil. So you want the unit to be producing hot water for your building, but the unit is doing exactly the opposite of what you want to do. So you want to do it for the less time that you can do it, and you want to do it only when you really need to do it. So most people will do defrost cycles based on time. When the ambient temperature is below a certain value, they will do a defrost cycle every 45 minutes or so, regardless of whether you need it or not. And this really, we think it's not a good solution because defrost will depend a lot on the region where you are. If you are in a place with a lot of humidity in the air, you have that water that's going to turn into ice in the coil. If you are in a very dry area, you have no water in the air. There's no reason to go into defrost because there's no water to turn into ice in the coil. So the temperature is not really the best way to measure defrost. So we do it based on suction pressure decay. Why suction pressure? We're doing evaporation on the external coils, so that's related to the suction pressure. And what happens when you start to have ice accumulation in the coil is that you lose heat transfer area in the evaporator coil. So you have less area for the air to cross. You don't have enough heat transfer between air and refrigerant. Your suction pressure will start to drop because you don't have enough heat transfer there. So we're always monitoring suction pressure and head pressure. And we see these lines that you see here, they're section pressure for the two circuits. And you see here a drop in the suction pressure. We have certain values, it's 0.6 bar related to a clean coil value. When you trigger that suction pressure decay, it means that you have ice in the coil and you are not being able to get enough heat from the air, so you need to get rid of that ice. So that's where we do the defrost cycle. Not based on time, based on the fact that the unit actually needs to do it because the suction pressure is dropping too much due to the fact that you have ice accumulating in the coil. Then there's another very important thing is that because we always have at least two circuits, the circuits are normally independent in terms of defrost as well. So you don't lose the entire capacity of the unit when you go into defrost mode. If you have a 100-ton machine, one of the circuits go into defrost, the other keeps running in heating mode. So this means that when the unit goes back to heating mode, doesn't need to recover as much as if the two circuits will have gone into defrost mode. So this is something really important when talking about heat pumps. And we see that in North America, a lot of people don't really have the best solution for defrost. They do it just based on time. And there's another thing about defrost is that in Europe it's actually mandatory to include a defrost penalty rate on the selections that you give to the engineers. So if you select a unit, let's say at 35 Fahrenheit, when you have a selection from Armec, you'll have a defrost penalty in the unit output. So here I'm showing a unit that gives you around 900,000 BTUs at nominal capacity. And at 35 Fahrenheit without defrost, the selection software will tell you the unit will give you 750,000 BTUs per hour. But if you consider the defrost periods that the unit will need to go, you will only actually get 600,000 BTUs out of the machine. So you should design the unit to this value and oversize it if needed, because you have a selection that will tell you, yeah, at the given point the unit is giving me 750,000 BTUs per hour, but it's not going to happen during an hour period, because at some point the unit will need to go into defrost, will lose capacity, and then we'll need to recover from that. So it's about 19% defrost penalty at certain conditions. And this is really important because you need to size the unit to give you the BTUs that it's actually going to give you in the field, not that you get on a paper at the specific design conditions. Yep.
Do a lot of your systems end up with, you use thermal storage, or are you just sort of modulating the output to meet load?
Well, we always need storage.
Mm-hmm.
And in heat pumps particularly, you normally need more storage than in chillers, for example. Because one of the reasons is defrost. You need to have energy storage to do the defrost cycles and to avoid that the temperatures drop too much during defrost cycles. Because if you have very small water volume in your system, during a defrost cycle that can last 6 minutes, the temperature can drop quite a bit. So the higher it is the volume, the less fluctuations you're going to have in the water temperatures. So yeah, the graph here, you're showing we're showing here on the top line is the living water temperature of the machine. This is in Celsius, so 55 Celsius, it's 131, I think. And you see it's a big drop in this case, the two circuits went into defrost at the same time. The temperature came up to 45, so you lost 4 degrees Celsius in the living water temperature. And then you take some time to recover to go back to 55. Yeah. If you do one circuit at a time, you see the drops is much smaller, and it's then easier for the unit to recover. The more volume you have, the less going to be the temperature drops in the system. Okay, so I'm gonna just talk about some case studies. We have a lot of these units in commercial applications, mostly in the West Coast, some here in the East as well. This one is in Vancouver. It's a Vancouver City Hall. It's a unit that was just installed a couple of months ago. 85-ton machine, provides cooling and heating for the building. With the pumps incorporated, you can see the pumps over there and the expansion tanks. And Vancouver has this target to go 100% renewable by 2050. So the City Hall is kind of giving the example, leading the way. It's a massive market for heat pumps and heat recovery chillers over there. And this is a solution that will provide a really high efficient solution to provide heating and cooling for the building. This is another one in California. This is a affordable housing job where we have, again, an 80-ton machine. In this case, it's a slightly different unit. We have a two-pipe distribution system in the building. Provides seasonal cooling or heating for the apartment. So the unit will provide cooling or heating for the building. This is a LEED Platinum job, by the way. And so you see you have two buffer tanks, one where you get chilled water or hot water for the space heating and cooling, and another heat exchanger where you get hot water for domestic hot water preheat. So talking about the multifamily housing, you always have need for domestic hot water. So if you have a unit that is giving you chilled water, why are you rejecting your heat outside if you can use that heat to do domestic hot water preheat for free? Even in the winter, when you're doing hot water for the building, you remember you have two circuits. So one of the circuits can be doing hot water for this buffer tank and the other for the other buffer tank. So you can still have an heat pump providing really high efficient heating for space heating and domestic hot water preheat. So this was a very cool job. We have quite a few of these in the West Coast. Over here, you will need a backup boiler, but still you can take advantage of the high efficiency of these machines for a big part of the year.
Okay, I'm gonna finalize the final slide.
That's okay. Question?
Oh, sorry.
Are the buffer tanks, is that something that you are included within the selection, or is that up to the design engineer to specify independently?
Yeah, normally we don't provide the buffer tanks, but we can help. We can tell you what's the minimum volume we need for the tank. So that type of information is easily available from us. We say for this machine you need whatever guidance for this system.
So you'll say like, you know, for this type of system, you want a system volume of X. Okay.
Typically, it's like 6.5 gallons per ton or something like that. It will depend on the unit size, because the more compressors you have, the more stages you have, typically the less volume you need. Smaller units, one or two compressors normally need more volume for short cycle compressors. But yeah, that's a number that we normally always provide, because it's, to be honest, I think it's the most important thing when talking about heat pumps is to have the correct volume in the system. To protect the unit, protect the compressors. So we see in the early stages, we've been doing heat pumps in North America for a while now. In the early stages, we saw a lot of systems with no volume at all, and that's asking for trouble very quickly, because it's not going to work properly. And installing a buffer tank later on, it's a lot of money. Installing it at the design stage, it's not a lot. But we have to do it.
So in this multifamily case, are you using the buffer tanks for domestic as well through a heat exchanger, or do you have separate potable tanks?
Well, in this case, our unit is going to an indirect tank,
Mm-hmm.
and they have potable water inside the tank. So you cannot have potable water straight into the unit because they don't have the
Right.
volume exchangers. So you
But
need
are you using the buffer tank water, does the buffer tank water go into the indirect tank, or is that
no. So from our unit, you have a coil inside the tank, right? So you're heating up the tank by
So
running
that is potable water in
in one of the tanks. Yeah.
Okay.
Yeah.
And so the biggest concern right now with doing air to water heat pumps for domestic in Vermont is that the first hour rating is so, like you just can't get a lot off of them. It's, you know, like you might get a first hour rating of 60 gallons.
Okay.
And that just then results in a huge amount of storage in order to meet domestic loads in multifamily housing or like food service or something.
Well, it could be tricky, yeah, but you might need to have a big volume and then just keep the volume at the design temperature, because well, the units are not going to be able to, if you undersize the unit, to keep up with the load and stuff.
It sounds like you can also preheat with it.
Yeah, exactly. Normally you do preheat and then you have a second lever to run it up.
You preheat with the heat pump and then you use a boiler too. Okay.
One of the challenges with a cold climate heat pump for this application would be that we're required to heat the domestic water to 140 degrees to prevent Legionella, I guess bacteria from forming. So you may, in the colder climate or colder periods of the year, not be able to make that, so.
Yeah, so you're gonna need the boiler to supplement that, or electric boiler or whatever.
Yes.
That's definitely gonna be the design for domestic boiler. Now, that's, might change pretty soon, because this is the latest technology we have available, and it is a solution for those applications where you need really hot water, domestic hot water. And we have the same machine, the same 4-pipe machine, providing cooling and heating for the building. And we're gonna add a second stage compressor heating to bring that water up to 176 Fahrenheit. So this is pretty much a water machine at 134.8 to be able to work with high condensing temperatures. And you're getting the hot water from your heat pump will act as the evaporator in the booster, what we call the booster. So this is the response to the domestic hot water needs. And in this case, you're gonna have a 6-pipe solution where you have cooling and heating for your building. And then you have this water machine that we call water booster to bring that water from 113 up to 176, and you can then do domestic hot water without the need for a boiler. So this is very, very new. It's something that was just launched a couple of months ago in the latest show in Europe. So we have just preliminary data, but it's something that we're going to start seeing more in the next year or so, and it's a response to the need to the domestic hot water with heat pumps.
What's the refrigerant type in the booster?
On the booster, we use 1 3 current. This is our 1480 and up. Yep.
Yeah.
What sort of combined COPs would you be getting for?
Well, for that stage alone, it's around 4. Okay, on the first one, it will depend on the temperatures, but we will be something like 2.5. But the second stage, it's really highly efficient.
Oh, okay, so, but it develops cumulative though.
It's cumulative. Yeah, of course. So, I don't know, I'll need to do the math. It will still be a lot more efficient than running a boiler, of course. But yeah, I can look into that and then give you a number.
It's one of the challenges with heat pumps is they don't really like high temperatures.
Well, yeah, but here it's we're talking about solutions specifically for those high temperatures.
Yeah, so your lift is only.
Exactly, the lift is not that big, okay? You're just working at the higher point, but the lift is not that big, so that's why you have a very big COP over there. It will definitely be much more efficient than the running boiler. Yeah.
So they're rated to -4, and you said that they can go a bit below. Is there any, for the North American market, plans in the works for low ambient kits? The only reason I ask is because January 7th and 8th this year, it was 20 below zero for an extended period of time. And so I didn't know whether or not that was in the works, or that's something you folks are looking at to get these more into the cold climates where we have those periods.
I don't think, as far as I know, there's no solution for that yet, unless using a backup electric boiler or gas boiler. Maybe if you use units that are that can only do heating, sometimes they allow somehow more flexible solutions. But if you want the unit to be a reversible cycle heat pump and do cooling and heating, you're really stuck to the operating limits of the compressor, and if you want to push it down, then it's not going to work in cooling. So maybe, as far as I know, I don't know of any solution that is in the pipeline for that type of low ambient temperatures. But if we're going to see something like that, it's probably going to be a heating-only solution. Because if you want to work at that extreme of the range, it's not going to work on the other.
Thank you. Do we have any questions on the phone? Responses? No? All right. Well, thank you, Daniel. So we're gonna switch this over. Are there any gurus in the room for Skype here? Because I have to somehow manage to convert this over. So maybe just a few minutes. Could you see if you could get Jake from downstairs, help desk, to come on up? I'm gonna do my best to figure it out, but I and not,
I'm looking on your screen right now.
yeah.
Hot water from one piece of equipment
But I think that's unlikely at this point.
without backup.
So I mean, you could.
I know, but the
set
thing
it
is
up.
like, if you think of like a,
That doesn't matter.
Something
Oh, wait, what are you
always-
looking for? The click,
something
oh,
that
clicker, yeah,
needs
yeah, yeah.
cooling.
Go ahead.
and open needs cooling quite a bit of a time, and also needs hot water,
Okay.
so food service.
That looks good, but I don't think you're actually presenting. So tell me when you see, yeah, no, I assume we're not there
And
yet.
we don't always need cooling.
Cooling hours are relatively, like still relatively small. When you think if they're looking at like, where's the -4?
It's
We're-
not
we're at
low
the
income.
fringe. Well, we're at the fringe too, for
Yeah.
temperature. So,
Yeah.
so it's,
While we are waiting, there is coffee over here if anyone needs a refill.
Right, what's like the default, like what's that? It's right around 160. So I'm just thinking, so you increase the cost of all your sales. So you can take somewhere, say 100.
Does that work? Okay.
We get started there.
All right, we're getting rolling again. Again, this is Benoit from Therm Atlantic, and out of, where are you guys?
Newfoundland.
Newfoundland.
Ooh.
A Newfie. So maybe the first Newfie we've had present to us, so.
I'm come from away, they say, so I don't actually come from Newfoundland. All the way from Brussels to Newfoundland to here, I guess.
Go ahead.
Okay, so,
Don't mind me.
okay. So I started a company called Therm Atlantic back in 2009. I was already involved in the, I guess this is a couple things. No? Sorry.
You just have to click back into the.
Trying.
Yep. Now that clicker should work.
Oh,
There you go, try it now.
okay.
Okay.
Can we hide the,
Yeah, that's what I did, and then
Unpin
somehow
it.
came back. And I did that, and it came back on its own, apparently.
You have to
Now
Move
click
it.
back into the presentation.
oh,
There we go. Takes a village.
okay. So basically, I had a company that sold in-floor heating products since 2000, and I recognized a few years after that, as heat pumps were emerging, that there should be a solution for heating water and, providing an energy-efficient solution for in-floor heating customers. So in 2009, we spun out our own line of floor heating products, and we also became the first distributor for a US-made air-to-water monoblock for Atlantic Canada. Within the first year, we ran into all sorts of problems. We discovered that, defrost and design water temperatures and flow rates and all sorts of nasty things were happening. So it basically forced me to rely on my previous background in IT as a programmer and whatnot to come up with our own controls to solve the problem. I also had to become an expert in hydronics real quick, and we came up with a solution that John Siegenthaler is quite fond of, which uses a three-way valve to act as a diversion valve in heating mode so that you can protect your buffer tank from getting too cold and a few things like that. The other thing that I did, and this was a decade ago, is I guess I released the first internet-enabled heat pump. So we were doing IoT a decade ago before it became an acronym. We attempted to actually license our technology to the US company that we were distributing the monoblocks, but they didn't really pay any attention to it, so we said the hell with it. And a couple of years later, in 2012, we just started manufacturing our own module. So what you should know about our product is that we do not make the entire heat pump. We rely on third-party, we'll call them condensers, but we all know they're evaporators and condensers. And our product basically handles the production of hot water and chilled water. But we do a lot more. We also manage all the hydronics, we manage the boilers, we offer the internet monitoring as well. In 2015, we were approached by a developer in the Halifax market in Nova Scotia, and he basically challenged us to develop a larger commercial version of our product for their multi-unit residential units. And so that winter, we tested a three-phase prototype, and as you can see from the next slide, it was quite a humble achievement. At the time, I was literally building the residential models out of my garage, so it really was a garage operation at the time. And my wife didn't like the idea of a big three-phase generator sitting in our driveway, so I had to build a doghouse that you can see there. Parked it in one of our dealers' lots because he had three-phase power. We put an Allied commercial 10-ton condenser on the roof, a 200-gallon storage tank, and our prototype inside the unit. And it was all being monitored, in real time over the internet. And over 3 months, we collected data at various evaporating temperatures and at various condensing temperatures. We had no load on it, so we had to keep chilling the tank to heat it up again. It was real fun. So once the data was approved by the client and his engineers, we basically, our first project, we jumped right in. So we went from building 5-ton units to 60 tons, all in the same year. So the first project, which I'll go over the case study later, was a 72-unit condo. It's also the first building in Atlantic Canada that we know of that uses floor cooling. I failed to mention that I'd been doing floor cooling for about 6 years in the residential sector, so I had a bit of experience with that. And it was a great success, and I'll be happy to answer questions later about how we made it work. The second commercial project we took on was right after the first one. It was for the same developer. It's a 40-unit seniors apartment building in Wolfville, Nova Scotia, about an hour away from Halifax. And that one uses a combination of in-floor heating and fan coils for cooling, which is certainly the safer, more pragmatic way of doing it. Later, we won a contract to install a tenant sub-metering system. So our company is very responsive to our clients' needs. We're client-centered, and we like vertical integration. So we recognize that within the multi-unit residential market, that people were also interested in tenant sub-metering. So they said, you got all this fancy internet monitoring stuff. Can you do that for tenant sub-metering? We said, sure. So we developed that, and the very first contract we got was for the tallest and biggest apartment building in all of eastern part of Canada, east of Montreal. So again, trial by fire forced us to get that product to work. Our third project was a 103-unit apartment building in Halifax, which also on top of that has a commercial retail level, about 5,000 square feet. It also uses floor heating with fan coils for cooling. The fourth project that we're just in the process of commissioning now is another 48-unit apartment building in Wolfville. It's a twin of the second project, except instead of using floor heating this time, they're using our line of ducted low-static fan coils for both heating and cooling in an effort to reduce their capital costs. And they also have our tenant sub-metering system. So this is a photo of our 20-ton modules. They're tandem, so there's actually 2 refrigeration circuits in this case, 2 10-ton circuits. It allows you to stage them, so we don't really need inverter technology at this stage because in this particular installation there's another unit you can't see, so they'd have a total of 8 stages, so you don't really need to modulate the compressors themselves. Upcoming projects that right now are in the works is another 48-unit apartment building in Wolfville. We have a 69-unit phase 2 addition to that third project, which will bring up the number of units. And then we have a large 150-unit apartment building in Halifax, which will also use our ducted fan coil approach. On top of that, of course, we were constantly exporting more product to the US and to other parts of Canada. This is just a summary of, I guess, what we've accomplished since we started. So again, we started with distributing a US product, a monoblock. We developed our internet controls and some of the hydronic things that we do. We began testing floor cooling in residential in 2011. We started manufacturing our own units in 2012. We started exporting, and we designed a smaller, more compact model. The first unit was great, but it was like took 2 people to hold it, and it cost a fortune to ship. So we developed a smaller one with a lighter heat exchanger. We released a product which really isn't aimed at the multi-unit residential market, but the brochure's there if you're interested. It's called the Distributed Forced Air System. It's an economical way of doing chilled water cooling in mid-range residential. Of course, then in 2015 we had that prototype, and we also released an 8 and 10 ton tandem line, which I don't really get into in this commercial presentation, but if you have large multi-unit residential projects with single-phase power, we can connect a number of off-the-shelf single-phase, up to 4 to 5 ton condensers to them, and yet concentrate the hydronics in one circuit, so it simplifies the installation and reduces the cost up front. We also launched, of course, our 20-ton tandem using 2 10-ton condensers. Then we launched our sub-metering platform. Last year we launched 20 and 25-ton condensers that are custom made for us by Aon in Texas. So they basically make mechanical guts to our specs, again designed for heating mode, and they install all our controls at the factory, so the units are ETL approved before they ship. We launched our sub-metering thermostat last year, which is actually a really cool project if you guys are interested in doing tenant sub-metering. Basically what it is, it's a PLC that looks like a thermostat. It actually does all the thermostatic control. It's networked, so you can have supervisory control. So if you have a 2-pipe system, you can all switch to cooling and heating at the same time, which is kind of a problem when you don't have that. But it's also a full-blown sub-metering system. So it has inputs for pulse water meters, for BTU meters, or you can do your own BTU metering using flow and delta T. We started stocking, we moved, I didn't put it in there, but we moved our warehousing and distribution to Halifax, Nova Scotia from Newfoundland because we couldn't really export from there. And we started stocking up on the Polar Air line, VCM high wall mounted fan coils. They have a full line of fan coils from high wall mounts, ducted, low static, medium static, high static, as well as some active convectors. And we're bringing in a couple containers every 2 or 3 months because, of course, the apartment building market uses hundreds of these things. We also launched this year in January our own line of 316L stainless steel water tanks. So we have 80-gallon for residential buffer tank. We have a 120-gallon indirect with 2 coils, and we have a 200-gallon buffer tank as well. We're selling them at much lower prices than what you can buy even carbon steel tanks for. And then this year we also, our last project is using our Duo module, which allows for concurrent heating and cooling. So we're able to do applications that require a heat pump to be whatever you want it to be. You want it to do domestic hot water, you want it to do chilling, you want to do heating. That was really in response to reducing the number of circuits in certain buildings to the point where we didn't have as much redundancy, and we wanted the ability to be able to, the system automatically do load balancing, but also be able to react to failures. I mean, when you have a large installation, you're going to have servicing issues. You have to be able to work around that, and this gives you that flexibility. So this is a photograph of the Aon line. It's a rooftop design. We found that these work really well with defrost. The wind doesn't affect them from the side or from the side with the compressor cabinet. And if you put them in line, the other unit protects them on the other side. So we found that these units performed way better than traditional, vertical discharge units used in the past. And it should be noted that the design that we gave Aon, doesn't matter if you go from 20 to 50 tons, we never go larger than a 10 or 12.5 ton refrigeration circuits. That again allows us to stage the units, but it also reduces the amount of risk. So if you have a problem, it's not going to knock out your whole system, it's only going to knock out one compressor and a small refrigeration stage. This is a photo showing some of the components for a tenant metering system. So we have first on the right, some pulse water meters. We import a line from Turkey. They're potable, lead-free models with 1 pulse per liter. The middle photo just shows some opto-isolated hubs that we're stocking, which allow people to have a more fault-tolerant wiring system so that you can home run each unit using Cat5 and then concentrate down to a hub in a mechanical or data room. And then the last picture just shows our very compact 16 by 20 panel. It includes a Modbus router. It includes a SCADA box running off Linux. And it has 2 opto-isolated hubs for concentrating the signals from all the different stories. So the biggest project we've got so far uses 350 units, going into one panel, but most projects are going to be smaller than that. The one thing I don't show here is the thermostat, but just trust me, it looks like a thermostat, but it actually is what feeds all the information to the units. The other hydronic products that we carry that I mentioned, so we have everything from low static to high static ducted fan coils. We have our stainless steel water tanks. Down below we have the high wall mount fan coils, just like the mini splits, except they work on water. And then a few other things I threw in there. We have BTU meters if you want to just use them for whatever application. The models we bring in have both M-bus wired and wireless built in, but we also had them put 2 extra wires for doing pulse counting using kilowatts, so you can actually use the same product with any number of different protocols or techniques. The final thing there, this little green thing, was an innovation I sort of came up with. It's kind of funny how products are invented or how you come up with them. So one of the projects, remember that big building I told you that we got the contract for? They had prepaid for all their water meters and BTU meters. And we sent them samples, and they gave us a check, and we went and ordered the stuff. And then a few months later, the owner comes back from Florida and decides that he's going to check on it. And he discovers that none of the samples were actually installed. And so he's on the phone, and he says to me, he says, "Benoit, where does this water meter fit? It won't fit in the radiator." And I'm saying, "Well, what do you mean? You put it in the wall." And he says, "Well, there is no wall. The risers are in the corner of the building, and they go directly into the radiators. There's no room for them." So I had to quickly come up with a solution of how was I going to measure flow or BTUs inside a radiator that was 3.5 inches in depth. And the solution was this little product here. It's part of a digital flow meter used for industrial applications, for water or for more viscous fluids. And I convinced the manufacturer just to manufacture the sensor for us. And then after a couple prototypes, we got them to do it with high frequency pulse. Our PLCs can handle up to 500 hertz, so we were able to do it. And these things, cost less than $20. So it's a really cheap way of doing BTU metering as long as you have 2 temperature probes. So that's what we use in a lot of projects now. Okay, let's talk about what we're supposed to be talking about. So what are some of the opportunities for air to water heat pumps in the multi-unit or the MERV market? Well, comfort. Comfort's always been the driving factor for floor heating, and floor heating has always been the driving force traditionally for air to water. Energy savings, of course, is a purchasing reason. If you're in an electric market, you're going to achieve more than 300% seasonal heating efficiency. And surprisingly enough, if you'd asked me 2 years ago where we were going to sell our products, I would have told you we'd focus on electric markets and in coastal regions with moderate climates. But the reality is that people are buying them in natural gas markets, and as we all know, gas prices fluctuate an awful lot, so these figures at any given point in time. But last time I checked, our systems, when sized according to our guidelines, were still 140% more efficient than natural gas. So there is a reasonable payback. The other thing too, which was really funny, and it started happening about 3 years ago on the West Coast in BC, Seattle, and Oregon, is that builders were contacting us, and they had access to natural gas, but they wanted to buy a heat pump, and the reason was that everybody wanted air conditioning. And they said, well, if we're going to pay for an air conditioner or a chiller, then why don't we just get a heat pump? So really the buying logic and the payback strategy sort of started to shift more in our favor at that point. So the capital cost realization is that if you need a chiller, air conditioning, get a heat pump, and then I'll just jump down one. The payback now is no longer just calculated on the equipment for heating. You can actually use a calculation that bases on the cost difference between getting an air conditioner or not getting an air conditioner. So if they were going to pay X number of dollars for the air conditioner, then really what we're trying to do is we're trying to pay back that portion of it. We always insist, I mean, the way we price our products, we're the lowest in the industry. In Canadian dollars, we sell for around $1,800 a ton. Most of our competitors, with better technology, mind you, are selling for $5,000 a ton. So we really want our customers to make money on and save money. The other thing I skipped there, of course, is that a good reason for purchasing is that today's consumer, whether they're an apartment building tenant or they're a condo owner, they want energy efficiency. We all want energy efficiency, so it's becoming fashionable, of course, to use heat pumps. And then, of course, the last thing would be incentives. Now, up until now, we haven't benefited from incentives very much, but we found, at least in the Nova Scotia market where we're active, that on average our customers are getting about $100,000 back in incentives for it. What's interesting is that, again, 10 years ago I started doing internet monitoring, and so I take it for granted that we know the performance of the heat pump, that we have a historical record of it for the entire year. And so even though our products didn't meet criteria at the time, the engineers had no problem saying, we'll submit you the data after a year and then we'll determine at that point whether or not it qualifies. And the result of that, as you'll see later, was that the first project we did got platinum LEED certification with our system. Yeah.
When you're talking about combined heating and cooling, are you still going with that floor cooling system, or are you talking fan coils?
Either way, we're basically heating or chilling the water, so you can do whatever you want. And we'll get into that. You'll see some hydronic designs in the case studies there. Maybe we'll answer that question. One thing that we run across a lot for competition, for advanced systems in new buildings is the VRF technology. And there's no doubt that the pro of VRF is that using mixed phase refrigeration, they're allowed for very efficient heat recovery. And of course, they also offer variable capacity, which is where the name comes from. But that isn't limited to VRF, and we can do it with staging. We can do it with an inverter. I mean, you don't have to have VRF to do that. The con, though, and John Siegenthaler, who just gave his day-long presentation yesterday, would be a big advocate of this. The problem that I see with VRF is, well, first of all, it's easily twice as expensive as what we offer. But the main con is that it requires, the copper piping throughout the building to meet the requirements of today's refrigerant, today's lubricants, and sized according to the pressures and whatnot. And, just putting refrigeration pipes inside a big building is kind of scary because it increases the risk of refrigeration leaks, which would be hard to find and repair. And of course, you'd have some issues there with gas in the building. And then the other risk about them is that when you have such a large network of high pressure piping, if there is a leak and there is infiltration of moisture or what have you, it can actually affect the entire system. So they are more vulnerable to failure as a result of that. The main reason, though, is that VRF is not future-proof. I mean, refrigerants are, they're already talking about phasing out R410A. So what are you going to do when, they're probably going to find a mixture that replaces it for the next 10 years, but then eventually all that copper in the building is going to have to be abandoned, or maybe they'll even have to remove it at their cost. So really, and then the last thing I mentioned there, and this is a bit of a pet peeve of mine because I come from the IT sector, is that none of the manufacturers that are doing VRFs or even mini splits are using a common communications protocol. So none of their equipment is interchangeable. In fact, within the same vendor's product lines, you can't interchange the equipment. So they're sort of like 30 years behind when it comes to using, IT software communication standards. So it really makes it difficult to think about, what happens if you have a building that has a bunch of heads, made by whoever, and you had to replace the back end of it, can you use the head with something else? And the answer is no, because, they're not going to talk. So I see that as being a big problem. So what are the benefits and considerations of using hydronics? And, you guys all here probably don't need to be convinced of this or you wouldn't be attending this presentation, but, a lot of people don't realize it, that hydronics can be designed for heating and cooling for a variety of different systems, including but not limited to water heat pumps. Floor heating again is preferable because it's a low temperature system, especially if you use a low mass design. Fan coils are ideal for zoned heating and cooling. Floor radiant panel can be achieved. Cooling can also be achieved as long as you have a dry climate or you provide dehumidification of the air so that the dew point can be fairly low. And then, of course, you can also use some of these European-style low-temperature passive convectors or radiators. I mean, you don't want to put that in a new building if you don't have to, but certainly in the retrofit industry, those are going to be quite popular. So generally speaking, low-temperature heating devices are preferable, not just because it makes it easier to use today's technology, but even if you do use a higher temperature heat pump, you're still going to get improved efficiency at lower water temperatures. So you may as well design for low water temperatures right from the start. I think it's important, though, especially in the multi-unit residential market, that instead of just doing heat loss calculations, you really want to be looking at heat gains as well. If you've got a building that's got a lot of glass, one side facing north, one side facing south, you're going to have a whole different equation than if you have a typical apartment building with small windows, and not much solar gain. So you want to qualify whether or not a lower and simpler two-pipe type of infrastructure is going to suffice, or whether you need to move to four-pipe so that you can provide cooling to one part of the building and heating to the other part of the building at the same time. Then, of course, you always have some hybrid approaches, which we haven't done any, but we're talking about it, and that is, if you do have a building that literally has a north and a south side, you could have two-pipe infrastructures, and instead of a four-pipe, and you could provide heating to one half and cooling to the other. But who knows? I just found that at least in the Atlantic Canadian market, there's a bit of resistance to going to four-pipe if they don't have to, so we've tried to address that as well the best we can with two-pipe. So what do we offer? Well, we're kind of a different manufacturer, we're a boutique manufacturer, and we know every one of our clients, not just because we sell directly to them, we don't, we sell through wholesale, but because of the internet monitoring. So we inevitably have a long-term relationship with all our customers, and we offer sort of systems integration services to the builders as well as to the engineers. So we offer our tandem, which is basically 2 stages, but they both have to be heating or cooling at one time. Or the duo, which allows you to do individual heating and cooling. We have our own OEM line of condensers made by AEON, or we can integrate with other products. So in the first generation, we use Lennox and Allied condensers, but anybody who makes a light commercial condenser, we can use it if necessary. We will provide or assist with the design of the hydronic distribution system using either traditional primary-secondary loops, or you starting to use low-loss headers. And you'll get to see some really cool stuff that we're doing with low-loss headers later. Of course, we can also provide, this version misses a part of the sentence. So we can offer the ECM circulators, the stainless steel buffer tanks, and the fan coils, and the flow metering equipment as well. Of course, one thing that we do that's different than everybody else is that we actually include the internet monitoring capability right out of the box. So you don't have to pay a controls company to develop it or to put it in. It comes with our equipment. And that'll basically give you remote control, performance monitoring, and diagnostics. What's interesting, and you get to see this at the end of the presentation, is that the performance monitoring we're doing, like in the residential market, is very limited. It just tells you how efficient your heat pump is. But once we got into the commercial market, where we had more I/O and more money to play with, we started to monitor not only the power plant, but also the load. So we actually know what the building load is in real time and historically, and we know what it is for the heat pumps. And they're two different things. I mean, they're not the same. And then if customers are buying into our tenant sub-metering solution, which is very affordable, not only does that give them, communicating thermostats and tenant sub-metering, but it also gives us individual loads now. because we know what every single unit is doing. And once you have this equipment in place, I mean, the sky's the limit what you can do with it. Maybe we could start doing load shedding, you know. I mean, we could do some really intelligent stuff with that data down the road. Yes?
Just a quick question about your hardware, because this is something I've run into with Canadian manufacturer before. Is your shop UL listed, so all the hardware is UL listed for the US market?
Okay, so I'll address that. We've actually been able to get away under the radar all these years because the module that we make, right, the indoor split module, uses 24 volts and that's it, okay?
Oh, really?
Yeah, there is no power going to it, okay? The only area that's a little bit gray was the control panel. So what we did with the Aon deal is that we ship them our controls and they have them ETL certified at the factory. So, so the units come pre-ETL certified.
Oh, cool.
If we do some fancy, you know, building automation work, what's usually required there is that we'll contract a local certification agency to do a field evaluation. Typically that's cost us around $2,000, $2,500 for an entire installation, and that's pretty cheap, you know, if you want to do that.
I only ask because in the last 3 to 5 years, the fire marshals have gotten a lot more strict on that, where actually on my commercial jobs at the final inspection, if it isn't UL stamped on the hardware, I have to give them paperwork that shows that it has all been marked, so.
What's interesting is that, I don't know how it is in the States, but in Canada, you know, anything under 33 volts doesn't have to be approved. But ironically, Nova Scotia in 2014 put in a policy where anything that has more than one control device has to be approved. And so even all our voltage panels are approved now because of that. And we get them locally stamped by QPS, which is like ETL, effectively.
Thank you.
Okay. Okay, so I was explaining to you that the data that you're going to get, you know, if people buy into our entire solution, is not just going to show the performance of the heat pumps, it's going to show you the performance of the building, and it's going to show you the performance right at the unit level if you buy into the tenant sub-metering. So there's a lot of people in Nova Scotia right now that are really want to get their hands on our data because they want to test the models, right? I mean, the models so far aren't that accurate, and nobody's really come up with a cheap way to get the data until we did.
And your, I forgot what you call your thermostat device.
Tenant sub-metering thermostat, yeah.
So those are all Cat 5 cabled to one location, or are they wireless?
No, well, they're not wireless. I mean, we could do that, but again, we're just using off-the-shelf components. Or actually what they are is they're Modbus PLCs that look like thermostats. And with any type of RS-45 device, you know, whether it's Modbus or BACnet or what have you, traditionally you daisy chain, right? You can go from multiple devices, and you can do that with ours too. So for example, in that really, really tall building, we daisy chain 9 units and then do a drop to an opto-isolated hub. But in most apartment buildings that you're talking, you know, like even up to the 103 unit one, they chose to home run Cat 5, and it's just because of the twisted pair. We only need one pair in a signal ground, but Cat 5 is cheap, so they use it. And they're able to home run that to a data closet at the end of the hallway, and then we use opto-isolated hubs to concentrate the signal down. So it's very flexible. You can daisy chain, or you can go star configuration, whatever you want to do with it. Okay. Where are we? Okay, and so I guess the last line about our offering is that unlike traditional manufacturing where they don't know you, they don't want to know your customer, well, we develop an intimate relationship with every building because we're the ones providing not just the building owner, the engineer, and the installer with data, but we're also providing it, you know, ourselves. So in this case here, we have a perpetual relationship using the internet monitoring platform. And nobody's doing that. I'm sure 10 years from now, everybody will be doing it, but right now nobody's doing it except us. Okay, so now we're going to switch to the case studies. So I'm basically going to give you guys a snapshot of the actual hydronic designs, and there's some large handouts that we could circulate. Actually, you're sitting there, if you wanted to look at them.
So, Benoit, I just want to make sure, we got 15 minutes left, so I want to make sure that you get a chance
Okay,
to
well,
do your
we'll have to run
lines.
through this quickly then.
Yeah.
Okay, so I guess I'll skip a lot of this stuff, but basically we're going to look at everything from floor cooling to fan coils for cooling to simple loops to low loss headers. We're going to look at how we've done domestic hot water as well, and you'll also see the evolution of using the smaller light commercial condensers to the larger multi-circuit versions. So the very first project is called Q-Lofts. It's a 72-unit, 3-story, 2-level loft condo. Uses ICF construction, triple glazed windows. They do floor heating and cooling with a concrete deck. It uses a centralized rooftop ERV, and it has a 20-ton coil that does the humidification for the building so that we can do floor cooling. It has a centralized tenant submetering system. It's different than what we offer now because they had already installed the meters and they already had thermostats, so we just centralized everything to one panel. They're using 3 20-ton DX2W modules with 6 allied commercial 10-ton heat pumps. They have 2 loops. They have a primary loop, which you'll see provides the chilled water for condensing for dehumidification in the summer, and then the second loop being the system loop, which is mixed up for floor cooling. We use 2 preheat 120-gallon tanks and 3 top-up tanks, indirect tanks. And then they have, where they were at the time, natural gas was going to be difficult, so they went with electric boilers for backup and top-up. And this project has achieved LEED Platinum certification. So this is a drawing. Originally, I did these drawings, more as a sales tool and to help design, but eventually they got used as drawings because in the multi-unit residential market, they don't really like spending as much money as possible. They like saving a lot of money. And if we can provide the drawings, they'll use them. The other thing is you'll find out if we have time is that we actually use the drawings as part of the human-machine interface for the monitoring. So if you get familiar with this during the process of building the building, it's really easy to then attach temperatures and flow rates to it. Okay, so again, this design, as I showed you, it's actually a takeoff off the residential design. So you have 2 10-ton stages per buffer tank, and then the buffer tanks inject into a primary loop, and then the primary loop can be mixed up in cooling mode to provide non-condensing water temperatures. The coil in the middle basically gets the condensing temperatures for dehumidification. Then there's a bank of boilers with a very simple loop, and then there's an injection loop for the backup or supplementary. And then in the other direction, you have the top-up tanks that are feeding off of the preheat tanks. The preheat tanks can feed either off the primary loop or from one buffer tank so that you can actually raise the condensing temperatures. And in the summertime, we don't have as much of a cooling load as a heating load, so basically 40 tons is available all the time for cooling, 20 tons is available for domestic hot water, and in the summer we can actually do all the hot water. The only top-up is just from recirc losses. This is a photo of the building. You can see there with the sort of penthouse on it. That's really just a big ERV in there. This is what the mechanical room is. A bit messy because it was our first one, but you see all of the indirect tanks on the left, and the modules are down the hall on the right, and the boilers are right in front of us. Second project we did was a 48-unit, 3-story seniors apartment, ICF again, triple glazed. It uses floor heating, but it uses high wall mount hydronic fan coils with a centralized HRV, so no dehumidification required because there's no floor cooling. It uses exactly the same number of heat pumps. It has a simpler design, which just uses a single loop because we don't have to produce 2 different temperatures. We use slightly less domestic capacity because of the smaller footprint and the slightly smaller boilers. So this one here looks very similar, but again, only 2 and 2 for domestic, and just one system loop with a bit of a bleed circuit so that the water can keep circulating to allow mixing to occur. This is a photograph showing the project, so hopefully the trees will grow and you won't be able to see the condensers in a couple of years. And this is the mechanical room here, so you can see our modules there. Each of those is 20 tons. And the buffer tanks are actually sized for 10 tons because we can drop it down to 1 stage when the weather gets warm. The third project is the big one. It's the 103 apartment building. It's wood frame construction, floor heating, again, high wall mount fan coils. An interesting note is that they had some concerns about using a 2-pipe system because you might have demand for cooling in most of the building, but the old lady in the north corner might need heating in the summertime. So we put in 500 to 800 watt electric strip heaters in the fan coils. And because we designed our own thermostats, we were able to have them intelligently allow someone to switch to heating in cooling mode, and it uses the tenant's own power to give them that little boost of electric. So it's a pragmatic solution to that problem. This one uses our 20-ton Aeon unit, so there's 4 of them in this phase, and in the next phase there's another 3 for 140 tons in total. This project uses low loss headers, which we're going to see in a second, which was really, it was again, need being the mother of invention. we had to put the condensers on the roof because there was no room on the ground for them. But because it's a wood frame building, they didn't have a concrete deck. It couldn't support all the weight of the water. So all the boilers and all the tanks had to go in the basement. And so how do we do that? You know, initially they wanted to burn the refrigeration lines down there, but there was just too much trouble with oil return and you know, the risk of doing that. So we basically introduced a low loss header. It was John Siegenthaler who suggested it. And you can see what the design looks like. So it's a vertical drawing. So this is the top part. So up on the roof, this is what we have. We only show one condenser there, but there are 4 of them now, and there will be another 3. So our modules basically have one circulator, one ECM circulator, which is responsible for running the water through the heat exchanger. But because we use big 6-inch pipes in the low loss header, there's so little head that it actually moves the water down to below. And so this is the bottom part of the drawing. And so you see the headers terminate at three buffer tanks. And then in between them, you can see the connection of the system circulator. So it basically tees off of the header. And so if we had a lot of time, I could get into this, but low loss headers are really interesting because they're biflow. They actually flow in 2 different directions. So if you're charging the tanks, you know, the flow is all in one direction. Then if you're running off the tanks, the flow reverses and goes from the tanks up to the building. And then once the set point drops, you have heat pumps staged. And every stage is about 40 to 50 gallons. So depending on the flow rate of the system circulator, which is driven by differential pressure, you can have situations where, you know, the heat pump stages are heating 100% of the building and charging the tanks. Or, you know, if the tanks are warm enough, the tanks are contributing while the heat pumps are running. So it's a very organic system. It also reduced the pumping energy by 60% compared to a conventional primary, secondary loop system. So we've actually eliminated so many circulators from this design. Again, here we're using a 1 million BTU natural gas boiler for supplement and also for top-up.
With the low loss header, is there any concern about, I guess you got to really watch the water chemistry, right? Because you won't have a fast enough flushing velocity to get any debris or anything out of scaling of the pipe. Well, I guess what was the pipe material, you know?
Well, they're just using carbon, but flow rates are actually quite high. I mean, we're talking a minimum of about 45 gallons and a maximum over 250 gallons per minute.
Oh, okay. Yeah, so when you max out, you'll move anything in the pipe anyway. Okay, thank you.
This is just a drawing I snarfed off the website of the apartment building, what it's going to look like when it's finished. Again, you've seen this. These are the first stage of 4 or 80 tons. That's showing you 60 tons. I'm trying to rush this a little bit, but there is a unit in the drawing there that can do domestic hot water or heating or cooling, and it has 3-way valves that allow it to switch between the primary headers, but then there's also a domestic preheat loop, which is a 3-inch loop. So maybe after the presentation, if you're interested, I can show you how we did that. And this is, I don't have any drawings of the finished product, so these are pictures I took while they were building it, so that shows you the 6 indirect tanks. These are the big 175-gallon buffer tanks. There's the 1 million BTU natural gas boiler. The last project, and again, I'm just going to flip through this really quick. Same as the other apartment building. The difference here is that they're going with tenant submetering, and they're only using ducted fan coils. And the design is using low loss headers. This is also the first installation using our dual units, where the complexity of piping is a reflection of the fact that those units can now heat or cool, and they can contribute either to the building heating or cooling or to domestic hot water. So you dynamically can make a heat pump do whatever you want it to do in this design. Here's some photos of while it was being installed. Okay, so now we have monitoring, and I don't know how much time, Jake, we have for this, but
We've got 5 minutes.
okay, well, how do we get out of this? So I'm going to get
Yeah.
into my presentation
Yep.
and bring up my browser. Okay, so what I have in front of us right now is that first building we were talking about. Now, as luck would have it, of course, we're at that transition period between heating and cooling, so we've actually turned off most of the heat pumps. There's not much going on, but there is a domestic preheat going on, and in fact, the heat pumps are running right now, so I can actually see that this heat pump here is currently putting out 41.1 kilowatts at a COP of 3.8, and if we had multiple heat pumps running, you would see the total on the bottom. And so if we want to look at the trend analysis for the last 24 hours, we can do it either location, but if we wanted to see the output, we just do this, so you can see the output is fairly high there. That's only for a 10-ton heat pump. And then the COP would be here. So again, it's quite consistent. Those little negative things would just be some forced oil return every 6 hours, a very, very short defrost cycle. I mentioned to you in the previous slide, though, that what was cool is that not only do we offer performance monitoring for every single heat pump and all of them at the same time, and of course simple things like water temperature. So here's the water temperatures of the buffer tank. But we also provide the load monitoring for the building. Now, of course, like I told you, right now it's in idle mode. We're actually providing no heat. There probably are still some thermostats that are running, so we're not going to get any exciting figures, but here's the actual building load for the last 24 hours, right? And there's a little secret here that if you guys haven't already figured it out, you should start using it. If you're using a smart ECM circulator and you're connecting it to Modbus or BACnet or what have you, you can use its internal flow measuring capability, okay? And if you're measuring delta T, bang, you've got BTU metering. So I call it poor man's BTU metering, but it means that every single circulator in our project, we do BTU metering with it. So again, if you wanted to look at the flow rate, here's the actual flow rates. And then here's the water temperatures, which of course are fairly low. There must be some solar gain here because the temperature's going up a little bit. And then over here, I don't know if you can see on the slide, but the coil, which probably isn't activated yet, they drain it in the wintertime, so they don't have to put glycol in it, but this is the circuit that's going to do the dehumidification so that we can do floor cooling. But you can see it, even right now, it's calculating a dew point of 51.6 degrees Fahrenheit. So the three-way mixing valve here would be mixing the water temperature at least 1.5 degrees higher than that. Although with a concrete slab, we don't even bother going that low. We don't go much lower than 60 degrees for floor cooling.
Do you allow people to open windows?
It's interesting. The way that this building owner did it, when they open their windows or their patio doors, it disables the zone valves on the system. Yeah. If you use our new tenant submetering thermostat, the dry contacts go into the thermostat, and it does it intelligently because we're able to use logic. We can say, okay, we're going to disable their heating or cooling, but if it gets colder than, 10 degrees Celsius, so probably around 50, turn the heating back on so we don't freeze the pipes. So, we can do it intelligently that way. Okay, so that's an example of what everybody gets for free with our system, and we usually use the actual drawing that we did on the design as the human interface. There are another 10 screens that are more technical. Like we actually do refrigeration analysis on every heat pump. We do this residentially as well. So every heat pump, the refrigeration technician can see liquid subcooling, you can see superheat. They see the output, of course, like we did in the COP. The input power, you can differentiate between outdoor fan power and compressor power. So diagnostics is amazing with this. I mean, you don't have to get out of bed to figure out what's wrong with a system with our technology. Okay, so now I'm going to switch very quickly to, except this thing keeps popping in front of me here.
The longer term time horizons right on this screen for monitoring, or do you guys that generated at a different page or report? Like you want to go back a week?
Oh no, we've got like from day one.
That's
so
all right here, you can pull.
From this screen here, we just automatically show the 24-hour trend analysis on a mouse over. But if you click on the point or you go to the other screens, you can go back and say, what was my performance for the whole year, and it'll do it for you. The trick is collecting the data, and what to do with it, you can evolve that over time. Okay, so this is what a typical multi-building owner would see. So Polycorp is the customer that's given us 3 buildings so far. So they have their own cloud set up for them, and if we wanted to do that HVAC stuff we just did, you click over here. And by the way, this is all smartphone enabled, so it scales to mobile devices very nicely as well. But if we go to the submetering, and we can go, say, to water and energy use. So one happens to be the super's apartment, so we get to take a sneak peek at what he's been doing. Of course, there's not much call for heating at this time of year, so I'm gonna go back and look at the last month. And it defaults to doing it by week. And then we can change that to by day. So basically the blue lines are cold water, the red lines are hot water, again potable, and then the green lines are their heating or cooling load. So you can see that on this particular day, which was April 15th, he peaked at 6.7 kilowatt hours for that entire day. What blows people away on this, I launched this at an AGM meeting where all the tenants were there, and I started asking people, how much do you think it costs to heat a condo? So I'm going to ask you guys, how much, these are 1,200 square foot condo units in Canada. What do you think it costs to heat it for a month, you know? Any idea?
$40.
After the heat pumps? Okay, so if we had a COP of about 3, that would be $120. With this building here, with ICF construction, the figures are closer to about $16 at the kilowatt rate, and then when you factor in the COP, it's closer to like anywhere from $8 to $11 a month to heat these buildings, right? It's amazing. It actually uses, I mean, if we had more time and we looked at a whole year's worth of data, you'd get to finally see what cooling really costs, because people don't really know. We all focus on heating, but it uses just as much energy at the peak cooling loads as it does for heating for most of these buildings, right? Okay, well.